Sure. Welcome everyone. And my name is Xiaopeng Li. I also go by Xiao, and I'm an assistant professor from the University of South Florida, the U.S. And it's my great pleasure and honor to host our traffic flow theory and characteristics webinar ISTTT 21 series. And before I start the presentation, I'd like to have a couple housekeeping issues. So if you notice that on the right ribbon there is a list of icons, that your default setting for the audio is on. I recommend that you turn it off until you want to raise a question, because there might be some interference and stuff like that. You can just mute it for now, except for the speaker. We're going to have a presentation roughly around about 40-45 minutes, and after that we have plenty of time to ask questions. You can raise your questions through the audio option, but also there is also a chat box. You can send your questions from this chat box to everyone, and that way, everyone sees it, and the presenter can address them sequentially. And also, I want to note you that the whole presentation is recorded, so just for information. With this, I would like to introduce the speaker for today, and today the kickoff webinar for the ISTTT 21st series is made by Dr. Jack Haddad. His presentation topic is robust constraint control of uncertain macroscopic fundamental diagram networks. Dr. Jack Haddad received all his degrees, BS, MS, and PhD in transportation engineering from Technion Israel Institute of Technology, Haifa, Israel. Since 2013, he is an assistant professor and head of the Technion Sustainable Mobility and Robust Transportation, or T-SMART laboratory. In 2010 through 2013, he served as a postdoctoral researcher at the Urban Transport Systems Laboratory, EPFL, Switzerland. His main research interests on traffic flow theory, control theory, and autonomous vehicles, which include management and control of transportation networks, traffic light control, optimal control theory, adaptive and robust control. In 2008, he was a visiting PhD student at the Delft Center for Systems and Control, Delft University of Technology, the Netherlands. He received the office of the Executive Vice President for Research at Technion, Grant 2008, for his PhD research, the Legate Award for Excellence in Teaching in 2007, and a student travel grant from IAAC, Israeli Association for Automatic Control. And he was a recipient of the Career Integration Grant by Marie Curie Actions. And I also want to gratefully acknowledge that he's a sponsor to our webinar. This GoToMeeting system is sponsored by the T-SMART laboratory. Without further ado, I'm going to give the presentation to Dr. Haddad, and thank you.
Okay, thank you, Xiao. I hope that you can hear me well. Do you hear me well?
Yeah, pretty good. Go ahead.
Okay, perfect. So first, I would like to thank Xiao Li for arranging this, and also Jorge Laval for his arrangement, and everybody. I'm really happy to be the first one in this series of webinar, and I will immediately for this year, and then we will start. So first, I will give a short motivation for this paper, this work. I will also explain after this the plant and the control MFD models. I will introduce briefly the interpolating control approach used in this work. Try to explain for an example, two region networks, some discussion, and I have also more extra slides. Well, in the next two slides, I will briefly describe some of the literature which are related to modeling and control of MFD systems. And actually, if you see here at the bottom, I have chosen some a short list of papers which can help me in presenting the motivation from this work, but there are much more in the literature related to MFD. So in the modeling, there are different aspects that we can take into account. So the first one is a network structure. So some works deal with the single region networks, while other works consider networks consisting multiple regions. Regarding heterogeneity, so some of, maybe somebody should turn off his mic because I hear him. Okay, I hear myself. Okay, so regarding the heterogeneity, there are some works that have treated heterogeneous networks by partitioning them into homogeneous regions, while recently a few works have integrated heterogeneity modeling in the MFD framework. And the dynamic equation based on MFD, which is mostly most of the research works, is related to the dynamics is relate the average traffic network flow versus accumulation, but there is other works that relate also total travel distance against total time spent. And regarding destination decomposition, we can distinguish between two types of models in this aspect. For example, in the first type, the regional accumulation in the dynamic vehicles equation are decomposed based on destination. What does it mean? It means that if we deal with one region, for example, we can write two equations for vehicles traveling inside the regions and vehicles traveling outside the region. While the second type of models, they don't do decomposition, so they look at the whole region without distinguishing destination. This means that one writes one mass conservation equation for the total number of vehicles inside the region. Now, regarding control, and in particular, perimeter control, which means that we have one aggregate controller on the border, on the regional border, that can manipulate the transfer flow that enters or exits the region. These perimeter control strategies have been introduced for both single and multiple regions. These control strategies have been designed according to different approaches, and one of the approaches, of course, classical approaches, which the classical approach, which I mean is classical feedback control, resulting in a PI or P controller or whatever, all these feedback controller. This approach operates according to the feeded information, of course, but without the need to predict the near future dynamics or demand. But on the other hand, it does not allow direct consideration of the control constraints. The constraints are usually imposed after the control design or after the design process. Now, another approach is more like a feedback and optimization. It's called the well-known model predictive control, which is, roughly speaking, it does not only include feedback, but also optimization. for a finite prediction horizon in order to integrate the future dynamics, or in other words, these kind of approaches are proactive and not only reactive points. This approach works well if the prediction models that we assume are sufficiently accurate. Now, recently we have introduced a robust control approach for parameter control by utilizing the classical robust feedback approach. And we have utilized QFT theory, quantitative feedback theory, to design parameter control. We designed a robust parameter control that can handle the uncertainty of the MFD. And what do you mean by handle uncertainty in the MFD? What is uncertainty for us in the MFD is that the MFD can have scatter of flows for the same accumulation. And in this work, the control constraints are explicitly integrated within the design level. We use a special approach, or what's called the so-called describing function. But the QFT, as we did it only for one urban region, because the QFT is suitable to design only, or it's suitable to design one urban region, but it might also be used for maybe two regions, but for more larger systems, it would be difficult to utilize. Now, the hypothesis in all this research is the following, that if the distribution of the vehicle density is heterogeneous, such that it affects the shape and the scatter of, or the level of the scatter of the MFD, so what we call heterogeneous network, then then there's two things. One, we can introduce improved macroscopic models that will be suitable to model such heterogeneous network. Second, robust, and I focus on robust parameter control strategies based on these models are suitable. Now, this paper, in this current paper, I mean, this hypothesis is only for not only the current research, for also follow-up research that I'm doing now in the lab. But in this specific paper, to improve the modeling, we aim at reflecting the uncertainty by considering the MFD as an interval function with a specific bounds. So instead of having one nominal blue function, we have some, because of the scatter, we can consider that it is within upper envelope and a lower envelope of MFD. This is what I mean an interval function. And then we can also reformulate. What we will do, we will reformulate the nonlinear model, because what we will introduce, the dynamics is nonlinear. We can introduce the nonlinear model, reformulate it as a linear model with parameter uncertainties. So we take out the nonlinearity terms by introducing uncertain parameters. Regarding the control, we aim at designing robust parameter control and integrate the control constraints in the design control by utilizing the interpolating control approach. Now, regarding the system or the dynamics, so what we have here, we have we will consider shortly the dynamics of multi-region MFD system. So let's assume that we have a network which is partitioned into regions, as you can see here, region I, region J, and R. And let us denote the demand QII, which is the demand from I to I, and QIJ is the demand from I to J. And let us denote that the number of vehicles that are traveling from I to I by NII, where the Nij is the number of vehicles that are traveling from region I to region J, and the total number of vehicles inside the region is simply Ni for region I. And the exit flow of MFD, we denote it by Gi, which is function of Ni. And regarding the perimeter controller, we denote it by Uij. So Uij is a perimeter control constrains the flow that can travel from I to J. Now, the dynamic equation is simply The dynamic equation is simply a vehicle conservation equation. And let's focus on region I, this region I here, okay, in the middle. And let's see what's going on there. So for region I, we have this equation, okay, the first equation here. We have first the QII, which is the generated demand inside the region I towards region I, plus all the sum here, plus all the transfer flows, all these greens, the transfer flows from reachable regions, which are controlled by the controllers, UGI, and plus all the, or minus all the internal output, which is given by this description. So we have, again, demand that is coming from outside, flow that is coming from outside. We have internal output here given by the MFD and these fractions, multiply the fraction, and this conclude the first set of equation. While the second set of equation, which is denoted by equation, is demonstrated by this figure here on the right, which demonstrate the number of the generated, we have the generated demand from I to J as an input here, and as an output, we have actually the output is the transfer flow from I to J, which is also controlled by UIJ. So what we have here, this is the output of the MFD, aims to travel to another region, to region J, and they are also controlled by the red parameter controller here, which is UIJ. By the way, the controllers, the parameter controllers, are a fraction between 0 and 1. 0, nobody can enter or transfer. 1 is everybody, there is no constraint on the control. And of course, you can put it between upper limit and lower. Now, this equation means that, as by definition of the definition of the variables, that the sum of all accumulation in the region is equal the number of variation, the total accumulation in the region is equal to the sum of all accumulation with all distribution. Okay. Now, this is clearly is a nonlinear model because the MFD, as you can see, MFD has a shape which is nonlinear. Also, the fraction here is given nonlinear. Now, why I'm emphasizing this? Because in the next slides, we aim at deriving uncertain linear models. So in order to use it for control design. So for control design, we utilize uncertain linear model. But for the modeling, we utilize, for running the model, we utilize a nonlinear model. So first, in order to get uncertain linear model, let's substitute these two equations into the third equation. And how we do it? We just differentiate the third equation. So we differentiate all the terms here. And we will put the first equation as the first term here after derivation, after derivative, and the second equation inside all second terms here. Now, once we do this, we get the following equation. We get one equation actually for region I, but what you can see still, we have one equation which depends on NII, NIJ, and NI, and still this network or this model, this function still nonlinear. Now, what we want to do is to extract the nonlinearity, and what we do, because physically also in transportation it would be difficult to estimate NII and NIJ, so the number of regions that are traveling from I to I, maybe if you have a lot of sensors, but it is difficult, especially trips inside internal trips, not traveling through the border, so it's difficult to estimate. So in this idea, what came to my mind is to introduce parameters. And these parameters is called, we call it destination decomposition parameters. So we denote all these fraction NII divided by NI by alpha I, and Nij divided by J by alpha Ij. And these are alpha are in between minimum and maximum bound, so they can vary within minimum and maximum values, but these minimum and maximum values can be estimated easily if you have some historical data. Now still, even if we introduce this, it is nonlinear, so we do linearization. So linearization around the set point. So we choose some set point. What do you mean by set point? Some point n hat and u hat. And then we rewrite all the nonlinear system here. We substitute by a new variable, which is the derivative from the difference or the derivative from the set point. So after we do this and we transfer to discrete function, then what we will get this equation, and this equation is uncertain linear discrete time system where k here is the time step counter and t is the sampling period. And the nice thing here that this is special system because A here, the matrices A and B are matrices which are uncertain depending on the parameters alpha, which is a vector of all these alpha that we we define. Now, the thing is simple. The control problem after this, the formulation of the control problem is simple. To solve this is more difficult, but again, we have the plant model, which is the nonlinear model, the previous model that we introduced, the original model, the nonlinear model, and for the control design, we have uncertain linear model. And now what we need to do, it is actually a regulating to region problem. What do you mean by regulating to region problem? What we mean, because we set here as a set point and we aim to reach these set points. So if we want to reach these set points, this means n of t should be close to n hat and u of t should be close to u hat. This means delta n and delta u should goes to 0. And this is what we mean by control theory regulating to region problem. So given the uncertain linear discrete system that I presented one slide before, manipulate the delta u, the controller, to bring delta n, the differences of all accumulation in all regions to go to the set points, or the delta n, it will be 0. But the important thing in this formulation that it should be works against all parameter uncertainties, not like classical control without uncertainty, but here is more robust control. So it should take all the uncertainties, all the alphas, or if you want, also the heterogeneity in the MFT. Okay. Okay. So how we solve this? I tried to utilize, or I utilized, and actually it's developing, it's still developed control approach, which is a new advanced control approach, interpolating control. So we do robust state feedback by interpolating control. And this approach, I cannot describe it all of it in detail, but this approach has the following properties, important properties. First, it guarantees robustness against all parameter uncertainties. This is what we want, of course. Handles control and state constraints, and the most important thing is that it presents also computationally cheap solutions. Now, what is the main idea? What is the main idea of this interpolating control? From the name, interpolating is to interpolate between two controllers. So the set of actions here.
I checked yesterday.
I got it today.
Okay.
Yeah.
Hopefully.
Yeah.
Okay.
Excuse me. Can
So
the
the set.
Excuse me, can the new attendees mute their microphones so that there will be no interference? Thank you.
Thank you. So what we do by interpolating two controllers. So if you see here the set point, the state space, you can see here two sets, one in blue, one in red. I will explain it in 1 minute. So you have one inner controller here inside in the blue, and one outer controller in the red. So we have two controllers. So the first controller is stabilizing controller with respect to control and state constraint, and the inner controller is a robust stable. So it goes to zero against all uncertainty. And in order to solve this by interpolating control, we can introduce two solutions, implicit and explicit solution. So let's more explain a little bit about the implicit solution. So we said, okay, we have an inner controller here in the blue. And the nice thing in this approach that we can utilize whatever control you want. So we utilize unconstrained robust, but it should be a robust asymptotically stabilizing controller. So we simply use a regular PI controller, simple PI controllers that can do the job. What do you mean by can do the job? That it is robustly asymptotic stabilizing. And according to this controller, there will be corresponding maximum robust invariant set. This is the set omega maximum, which is the set of all x's here in the blue. And what does it mean? This should first include the origin, as you see here, include the origin. Second, it should satisfy the constraints for all x inside this set. And third, if you are inside this set, all the next steps of k plus 1, the state will stay inside this set. This is what we call robustly invariant set. Now, once we have the controller and we can build this set of omega maximum, maximum invariant set, we can also build or calculate the sigma Cn, which is robust n-step control invariant set. And this robust control invariant set is a set of all x, so all x here inside the red, satisfy the constraints, and for which there exists a control sequence that can bring you or can drive you from the set Cn to inside sigma in no more than n steps. So again, if you are here in no more than n step, 1, 2, 3, 4, no more n step, you will enter to the sigma max. Now, how we calculate this, I cannot go into details, but I refer to two references here in the literature, so you can know how we calculate it. But again, first you assume a controller, and then you calculate sigma max, and according to sigma max, you build the C. Now, the idea is that once you have this, any state, current state, x of k here. So, and what do you mean by state? State here, I call it x, but remember that the state of the system is the number of accumulation in the regions, okay? It's the set of all the number of accumulation in all regions. So any state x here inside the Cn can decompose in this following formula: simple interpolation coefficient multiply sum xv plus 1 minus c multiply x0. Okay. Now, why we do this? We do this because we want to calculate the best control at x. So the best control at x, the idea says that it should be interpolating by the input controller here at x0 and then input controller by here optimal controller at xv. So first we decompose it like this, and then we say, okay, and this is proven in control theory that the control law here at x, u of k, is actually equal, if you take this control, that it is equal to the same coefficient here that you decompose the state, So C of k multiply UV plus y-1c. It's the same coefficients, okay? This control guarantees robustly asymptotic stability for all initial states. So if you apply this control at each time step for each x, you will eventually go to the 0, 0. You will eventually go to the origin. Now, what is the controller U0? Controller U0 is all the control here inside the inner controller. And the inner controller, we chose it in advance as a p proportional controller, as you can see it here. And the UV, which is outside in the outer controller, is the so-called vertex controller, and we need to calculate the vertex controller. So I don't explain how we calculate the vertex controller for XV, and I don't explain how we calculate C, because we need to calculate C in order to calculate X and then U. In order to do this, we need to solve two LP problems. So LP problem 1 is the decomposition of the state X here. So we calculate exactly what is C of K. And the LP second problem is to generate the vertex controller. So what is the UV for XV? I don't explain it here. If we have time, I have more slides and we can explain it later. Now, the explicit solution, regarding the explicit solution, this is implicit solution. What do you mean by explicit solution? That each time step, you have to solve this 2LP problem online and apply the controller and move on and so on. But there is another option. This is a nice feature of this interpolating control approach, that we can calculate. Instead of computing at each time step the control as a function of the current state X, the control law can be a priori computed offline as an explicit form, as a piecewise affine state feedback over polyhedral partition of the state space. What does it mean? I will show in the example. If it's not clear now, don't worry, you will see in the example. Okay, so now let's take one example, and the example is we took a two-region network. So we have two region, two MFDs, and we don't take the whole range. So we don't take, of course, from 0 to n max, for both regions, because the idea is that if we succeed to design a robust controller for the whole set with uncertainty, then the controller will be, or expected to be, very conservative, resulting in poor performances. Why? Because you take the whole set, the whole options, from 0 to n max. You can do it, but again, it will be very conservative. So what we decide to do is divide the cases to special cases, mode 1 and mode 2, that we believe that are more recurrent situation in traffic, for traffic condition. For example, mode 1, both regions are regulated around the set points, which is on the congested regime here. This is N1 hat, N2 hat. And the other one is that one is in the, you need to regulate one on the uncongested and one in the congested. Well, for the mode 2, it is clear for us that our goal is to be far away from the congested regime. This is clear because it's unstable and lead to gridlock and so on. But sometimes during the peak hour, and actually when the demand is too high, we might aim at regulating around set point for a temporary time near the critical accumulation here, in order to prevent the system to be more and more congested and go to gridlock. So this is the reason that I also try to analyze mode 2. Now, if you take for this is example 1 for mode 1. We took N1 hat and N2 hat into 3000. I remind you, 3000 is here. This is critical around 4000, so we are in the uncongested regime. And once we do this, we took uncertainty for the alpha between 0.3 and 0.7. So it should take into account all the possibilities of alpha. And the accumulation, we did some accumulation which is in the region nearby the set point, which is between 1,500 and 3,300. What you can see here, we can have we plotted the maximum and control invariant set, and what you can see here, we choose again from 1,500 to 3,300. So at the x-axis n1, all the state, possible state, admissible state are covered. This means that covered by red. This means that each state inside this region, 1,500 to 3,300, can be stabilizing, because you have such control that can bring you to the controlled invariance, maximum invariance set, and then go to the set point, which is here, 3,000 and 3,000, as you see here. It's going here. So these are the figure for accumulation trajectory. So as you can see, it's going, okay, it's converging. It takes some time to converge, but it is converging, of course, because we have high uncertainty, so it will take more time. Now the control, it starts from 0.1, so it is preventing flow or limiting flow traveling from 1 to 2, and then it goes to 0.6, and this is the coefficient that I talked to you about. So this is the interpolating coefficient between the outer and inner controller. It starts with high for the inner, and then once you enter, sorry, for the inner, and yes, for the inner, yes, and then once you enter, it will become C0. So only one controller will work. Now for the mode 2, we have the same okay for the mode 2, 3,000. We took 3,000 and 4,000 for region 2. Similarly, but what the nice thing here that you see that look at the state of X of N1 of the accumulation and N2, it is not all the state is by red, covered by red. This means that if you are here, the system will be not stable. I mean, with the current situation, if the demand does not go down, if the demand is still high, you cannot do anything. You need to wait. This is going to gridlock. And actually, this these nice regions, it's very helpful for transportation engineering guys also, for the engineering point of view, because you can know more information about the system. We have also another paper called Stability Analysis that we already published in Transportation Research Party that deals with this kind of issues. If somebody is interested, I can send you an email. But again, this is a linear model. In that paper was nonlinear model. And the nice thing that you can see that we have the same, we can have almost same regions. But what you can see here, okay, initial condition, and again, it goes to the steady state that we designed, to the equilibrium that we wanted. Now, the explicit solution, and this is I really like. Actually, I didn't believe that I will get it because of the number of regions, but because for 2 regions is still okay. So as you can see, we calculated offline the optimal control, and for example 1. And what you can see here, you can see delta N1, the difference here, delta N2, and this state is partitioned to 5 regions, 1 small, 2, 3, 4, and another one here in the corner small. And for each region, okay, look at the down here, the control input depend, you have control input which is a piecewise function of the state. So the x-axis here, delta N, delta N1, and delta N2 is this figure. And according to where are you in the state, you just go and plug in this piecewise function, and you can have the control, and this is calculated offline, and you just want in real time to see where are you. What do you mean by where are you? That each time you check delta n1 and delta n2, delta n1 and delta n2, and you check in which session you are, in which state you are, in which part you are, partition you are, and then you just plug in here and you will get the control. So this is faster than the implicit solution, which is also fast, by the way, because it's linear programming, but this is would be much faster. It will take some time to figure out where the state which belongs to which to which region, but it's we have also very good algorithm for this. Now, if we compare it very fast, if we compare it with other controllers in the literature, so what we have, what I did here, we have implicit interpolating control, okay, implicit interpolating control, explicit interpolating control. We have the MPC controller, which I implement MPC controller according to another work that we already published in this area. And we utilize also LMI controller, which is roughly speaking is a way to solve robust classic controller that is also designed in one of the papers. So we wanted to compare and see positive or negative perspective of this interpolating control. What we see by implicit and explicit controllers that there are similar results in control input. This is a control input and this is a compilation. Even it's very hard to see, but they coincides here. The two lines, the cyan and the purple one. But the average computation time, of course, the implicit takes more time, 14.2, while the explicit takes 6.84 because it's already calculated offline and just searching here 2LP problem. Regarding the LMI controller, if you look at the LMI controller, where is the LMI controller? Yeah, the LMI controller, actually, the LMI controller also coincides very fast and similar to interpolating controller, which is good. We are happy with that. But if you look at the control input, and this is the control input of the LMI, you can see that it violates in the beginning. It's really violate the constraint of the control. So U12 is go less than the control input constraint, which is 0. It cannot go minus, but it goes minus in the LMI because there is no consideration for the control constraints, and it needs to act very strongly, so it's violate the control. So it's in the beginning violate the control. If we truncate the controller, we will have bad results for the LMI. Now the MPC controller, this is the green one here. And what you can see immediately is overshoots. You can see large overshoots in accumulation. The MPC converges faster. Look here, converges faster than the interpolating control. So it goes to the 3000 faster. And the computation complexity of the MPC is more complex. Now, if I want to summarize, so the main contribution of this paper is that the nonlinear vehicle conservation equation are transformed to linear equation with parameter uncertainties. These parameter uncertainties include the destination decomposition fraction, which are difficult to estimate in reality, and also you can integrate the scatter of the MFD. The uncertain linear model utilized to design robust feedback controller by the interpolating-based approach. The robust control is presented as implicit and explicit solution, and the comparison results demonstrate the performance advantages from applying the robust interpolating controller. That's all. I have more slides for discussion and more slides for more explanation, but I think maybe it should give some time for questions. And what can I see that Shao has left because he has another meeting, and I need to handle the question. So please, if you have some questions, let me know. You can write down in the message here, or if you want, you can ask using the microphone.
Thank you, Jack, for an interesting talk.
Oh, Jorge, hi, thanks.
All right. So let me start with a question about the MPC approach you showed. So
Okay.
You mentioned that your method allows it to converge faster.
The MPC converge faster than my method. And the reason is that MPC, we should remember that MPC has an optimization criteria. So in each time step, you do optimization. I mean, if you to reach, let's say, to reach the destination or another objective function, but you have an optimization function. Unlike my approach, or not approach, my approach is I just implemented. Not like the interpolating approach. With the interpolating approach, you don't have at each time step an optimization. Okay, you have some LP problem here that you need to solve in order to decompose. The decomposition take into account what is the optimal C in order to have the best solution or decomposition between x0 and xv. But still, it's not a direct optimization function for the tracking or for going to the equilibrium or to the steady state solution. So this is the reason that the MPC definitely, I mean, it's not surprising for us. In some cases, it will have more convergence than the interpolating control. See here, it converges better. But we shall remember that in this case, MPC, we assume a very good model. So the model that we utilize it to calculate the control, and the model that we run the control for it are really very close. This is what we mean. The prediction model is good. Otherwise, you will not see good results or conventions like this. So in my case, I tried to choose a really very good close model and plant and control model in order to be fair in comparison, or in order to take the extremum of this interpolating control approach and to check it.
Okay, I think I got it now.
Can you explain the equations for LP2? Let's try. Hi, Rama. Okay. Yes. So the LP2, let's start with LP2. What is LP2? LP2 is UV here. So it is the vertex control law for the state XV. Okay. So let's go a little bit I have slide here actually. I hope so. This is LP1. Yes, I think yes. Yeah, this is the LP2. So the idea is that you have the whole so you have the CN, okay? The CN is the red one. It's here, it's not covered by red, but assume that this is the CN. And now the CN can be decomposed into a set of simplices. So we have here 1, 2, 3, 4, 5 simplices. And in each simplices, you see here you have x1, x5, and you have controllers, u1 and u5. So these controllers, you can calculate it. And in these controllers, if you apply, so if you are here in x1, if you apply u1, it definitely will take you inside the set. And if you are xv and you apply uv, it's also give you take you inside the set. Okay. So in order to calculate what is a control here, which is uv, it's not written here uv, but this is what we mean. The control vertex control at the state x. This should be, look at the equation here, should be some weighting between all the vertices controller here, u1, uv, and the origin. As you can see here, sum from I to p or I to 2, si multiply ui. Okay, so it should see some interpolation actually between u1 and u5 in order to give you the best u. This is a simple idea. What is the best u? That it's guarantees that it will take you again inside towards 0. Okay, now how we calculate si? We calculate si according to the states. So we make a minimum of this coefficient, all coefficient, according to this equation that the state is a combination between, again, x1 and x5, the vertices. Okay, so it's the sum si multiply xi is equal to xv here, and these are the combination, and we need to minimize the linear programming. This is it's well known actually, vertex controller. The first work, if I'm not wrong, is 86. I have the paper, I can send you the paper. So these are the vertices of the simplest Cn, and by this you can minimize this objective function, which is the sum of the weights, I call them, and you can get them. Okay, once you get them, we utilize them as an optimal solution also for the combination of the convex combination of the vertex controller here by this equation. Okay, did I answer your question, Rama? Okay, good. But if you have more question, I think you can see my email here or in the website, and I'm happy even to talk about this more. I mean, it's very difficult to explain in more detail in 1 or 2 minutes, but we can discuss it more if you want. I'm happy to discuss it more. I can send you also the paper which is related to the vertex control. Okay. Is there any more questions? If not, I can have here a brief discussion. Maybe can raise some question. Well, I put here some brief discussion on some issues that during. Okay, Rama. So you repeat both LP every time step, and does not that give you? What do you mean by oscillation, Rama? I mean, no. It is okay. There is a lemma in the book of Nyguen that this will bring you by LP1 and LP2, that this will bring you inside inside the sets, and eventually it will guarantee the robust asymptotic stability. So this control law, I don't show the proof. I don't have it here, but it is proven that eventually it will go and guarantee robustness, stability, sorry, asymptotic stability, taking into account also the uncertainty. Again, by the way, I can also send you, if you are interested, I mean, I don't know, if you are interested in this, yes, of course. I can also, let me see the paper. Okay, I will send it. Please send me the email. I will send you this more privately, or so I can send you the author of this book meanwhile, and then so it is a new book by Springer, 2015 or 2014. I think you can download it, and the proof is there. Now, let me complete. We can have 5 minutes more, because this is really nice, because some of the discussions I came up after you work in this in details. Well, in one hand, I introduce here uncertainties, and it was nice because it's really simplifying the traffic modeling. I mean, it decreased the number of states. So if you remember, we had NII, NIJ, NI, and then eventually I end up for region I only one state, NI. So you simplify the traffic modeling by decreasing the number of states, because you say, okay, all the other is parameter uncertainties. Estimating, and this I already mentioned, the uncertainties is helpful here, because it's very difficult to estimate the destination decomposition. But the issue is, in a control point of view, that handling parameter uncertainties in control process is not a trivial task. And I felt this when I utilize traditional robust feedback control approach like QFT and other, I'm just mentioning one of them. It's more difficult when you'll have more and more regions. So one region, two regions is okay. One uncertainty, two uncertainty is okay. But when you have more and more, it will be more difficult. This approach, interpolating control, I must say that it's really helpful in order handling much easier the parameter uncertainties. But if you add more and more uncertainties, you know that the controller will be more and more robust and far away from optimal control, optimal solution, and then you might come up with a very, very conservative control. Then it depends on in what your control purpose. Regarding the interpolating control, we say the properties guarantee robustness. This is I mentioned. So this is positive, handles control constraints, this is computationally cheap solution. The interpolation control performs better than the designed MPC. Instead of, I mentioned that as Jorge asked, it converged. The MPC converged faster, but I forgot to mention, and very good that I remember now, look at the overshoot. So in order to converge faster, it makes overshoot, large overshoots. So the state should go to 3000, goes to 1900. If you accept this, which is a little bit problematic for engineering, because you go down to 1900 in order to reach to converge faster, but not much faster than the interpolating control. If you accept this, do it. But again, in my opinion, these overshoots are I don't really like them, and this is the reason that I mentioned here that the MPC, the interpolating control, performs better than the MPC. And the only issue that I already mentioned by the answer to Jorge, that the interpolating controller does not integrate an optimization criterion. So our goal is like any feedback control, classical feedback control, to regulate some values, some state values, some accumulation to predefined specific values that we believe if we go there, the solution will be optimal, because it will be on the top or in the maximum flow of the MFD. But there is no optimization criteria. Now, regarding the CN, the nice thing is that it is characterized as stable and unstable regions. Computing the CN, the red regions, might be time consuming, and actually it takes time. So you need to wait in order to calculate the CN. But in the interpolating control, it doesn't matter, because you can pre-calculate it offline, and it's only, you need only to calculate it one time, according to the control that you assume to be in the inner controller, what you assume in the inner controller. Once you define the inner controller, you can compute this for one time and offline. So if it takes time, it doesn't, you should not care of that. Okay, so that's all. If you have some question now, after my brief discussion here, I would be happy to answer.
All right, thank you, Jack. Such a good discussion there. So with this, I think we can adjourn. Just say that this series is going to be quite interesting. We have currently more than half of the speakers already expressed interest in participating. Actually,
great.
So we'll have webinars for a year, all right, of the ISTTT series. So hopefully we'll see you all there soon, most likely next week. So stay tuned. And thanks again, Jack, for your participation.
Thank you very much for this opportunity, and I appreciate that such a webinar is given by the TFT committee, because you know, it gives you some information of the recent work that is done in this area. Thank you very much.
Alrighty. Bye-bye, everyone.
Bye-bye. So the student of Shao, can you stop recording, please?
Yes, I will do that. Thank you so much, Dr. Haddad.
Okay, perfect. So you take care of the recording.
Okay,
Thank you. Bye-bye.
Bye-bye.